All right, welcome back to our lab. So today, our lab is going to be dealing with the relationship between the electric field that we've been learning in class and what's known as the electric potential. So the first question then is, well, what is the electric potential? Well, recall from Physics 205 that the work that a force does from bringing a particle from point A to point B along some pre-described path along this dl is then equal to the integral from A to B of the force dotted by the differential length, but work is related to the potential energy by minus the potential energy. Now, what would happen if this force, which is doing the work, happened to be the electric force? Well, in this case, we know that the electric force then is going to be the charge times the electric field, which means we're simply going to replace this force with the charge times the electric field, so that Q is going to come out. So now it's just the integral over the electric field instead of the electric force. Now, from here, it's convenient to define a new quantity, which is known as the electric potential. So electric potential is denoted by capital V. So notice when I do capital V for potential, I'm going to put a V with 2 bars on top versus when I do a volume where I do one continuous line on top. Hopefully you can pick that up. But we define the electric potential, which is then equal to the potential energy at a given point per unit charge, which means the electric potential, V, has units then of energy per charge. So, here, there we go. So let's move this down. So what does this mean? So this means then that minus the change in potential or electric potential is then equal to the integral from A to B of the electric field dotted by that differential length. Now, delta V is what's called the electric or the potential difference, also what's known as the voltage. So why do we use this? And why is this important? And how is it actually related to an electric field? Well, first off, we use the potential because it's something which is easy to measure. So when you take a voltmeter and you measure the potential difference between 2 points, you're simply measuring this guy, and it's nice and easy to measure. The second thing is electric potential, because of this dot product here, this is actually then just a scalar quantity, which means that this thing doesn't depend on direction. It only depends on the distance I am away from 2 points. So it only depends on that magnitude. It doesn't depend on if I'm going one direction or the other direction. It has no directional properties associated with all. And the other reason we use this is because this guy is directly related to the electric field. So how is this guy related to the electric field? Well, we have what are called equipotential lines or equipotential surfaces. So what's an equipotential surface or equipotential line? So they are lines or surfaces of constant equal potential. These lines actually tell us about the electric field. Now we'll establish this more in class when we actually talk about it in class. But it turns out that if we know what the equipotential surfaces look like, so here what I have is actually 2 charges. One's a positive charge, one is a negative charge. And then these green lines here are the equipotential lines. So what this says then is that this is 5 volts worth of potential difference relative to this charge, which is at 0. So this is at 0 volts. This line here is all points that are at 4 volts. This line is 3 volts, 2 volts, and 1 volt. So it turns out that if we know these equipotential lines or these equipotential surfaces, the electric field itself is actually perpendicular to these lines at all different locations. So what that means then is my electric field then, so all I have to do here is draw perpendiculars which go through each one of these lines. And this establishes actually what the electric field looks like. So each one of these are at 90-degree angles. Moreover, it turns out that the electric field then points from high potential down to low potential. It's actually equal to minus the gradient. So it turns out, we'll talk more about this in class, that the electric field then is equal to minus the derivative of the potential with respect to position. So this is in the magnitude in 1 dimension. We'll generalize this to multiple dimensions. But so this negative sign means that it points in the direction of opposite the change of increase, which basically means it points from high potential down to low potential. So what this says then is if I simply know these equipotential lines, I can then map out what exactly the electric field lines look like by simply drawing these perpendiculars. And then the direction of the field itself, again, is going to point from high potential to low potential. So my electric field is actually going to do something like this. So this is my electric field. So So what's the point of all this? The point of it, again, is that we can actually easily measure the potential because we have a voltmeter. That's what the voltmeter does, is it measures the potential difference between 2 points. Now, the point about that is exactly the same point as with potential energy, is it only tells me the difference between 2 points, not what the value is at any given point. So this just means that this is 5 volts relative to this point. That's what this tells me. So, but again, the point of this is that I can easily measure potential differences, and then once I map out these equipotential surfaces, I can then easily extract what the electric field looks like by simply drawing perpendiculars to all of these points, connecting them all together to then establish what the electric field looks like. So again, the reason for this is that the potential is a scalar quantity. That means we don't have to deal with vectors anymore. It's easily measurable, and it has a direct relationship to that of the electric field. So in this lab, we're going to be looking at that by playing with this system here. So this is our experimental setup for this week. So here we have a power source. So here's my power source. Here we want to make sure this is connected to DC, not AC. DC means direct current. This side over here is AC. So basically from here, we're going to run one wire from the negative terminal to another wire to the positive terminal, and then go ahead and turn this thing on. And what that's going to do is it's going to set up a potential difference. So the negative terminal, it's going to set this guy equal to 0. This side, it's then going to equal to whatever it is that I set this thing at. So this thing is roughly set at, looks like a little bit below 6 volts, so maybe around 5 volts or so. So there should be about a 5 volt potential difference across here, but we're going to use our multimeter here or a voltmeter to measure that. So here, this thing is a conductive paper. So basically inside of here, it's allowing charges to move inside of here to establish this potential difference. And then here I just have these metal, what do you call those things? Paper clips, or not paper clips. Tacks, there we go, that's the word I'm looking for. So I'm pushing this in here, and then I'm going to put up the paper a little bit. So on the paper, you can actually see a little mark on here. So this is actually made with a metallic pen that's actually drawing on here. So I'm just pushing through the tack in enough to make sure that I'm making direct contact, and then I'm going to click my alligator clip onto here. Now from here, to use the voltmeter, I have to use 2 wires. The first wire I'm going to plug into the middle one here, which has volts, ohms, and milliamps. I'm just going to hook that into there. So this then is going to be the negative side, so I'm going to plug that into my 0 terminal. The other one I'm going to hook into COM. Now, depending on which multimeter you use, it's going to be slightly different, but you definitely want one plugged into the voltage, the other one plugged into COM. And then what this is going to do is it's going to measure the potential difference between the two. So for example, if I touch the prong, which this is at, it should read 0 because I have 0 potential difference because I'm touching the same thing. But if I touch the other one, then I'm going to measure a 5.5-ish potential difference. So that means there's potential difference between here, which is the 0, and this one, which is at 5.5 volts. Now, all we're going to do in this lab then is you're going to have an extra piece of white paper, which has exactly the same grid on here. And then what you're going to do is you're going to look for these equipotential lines. So for example, I'm going to put here, and I'm going to measure potential, slide it down a little bit. Let's try to get the 2 volts. Okay, so that's about 2 volts. So from here, you're going to put a mark on your paper. So this is happening at about 10.510. Okay. So on my white paper, I'm going to put a mark at 10.510 and call that 2 volts. Now I'm going to move around to try to find another point over here, which is also at 2 volts. So that's roughly about here. So this is happening at about 9 and 6. Okay. So map out about 6 to 10 points all along that particular line, which has constant potential difference, and then find another line. So for example, if I look at the center point here, the center point has, try to find a 3 volt one. So 3 volts would be about here. So that's roughly almost 1510. So I'm going to look for all points along here, which then have 3 volts. So those are all written in the manual here. So basically, again, when I find a point on here, I'm going to map that point to the white paper. From there, I'm going to find about 6 to 10 points, which all have exactly the same amount of potential. I'm then going to map out those potential differences to then find the equipotential lines. Now, again, once I get those equipotential lines, Sorry to spin it that fast, so nobody got sick. So once I know the equipotential lines, then the next part of the lab then is establishing what the electric field looks like by, again, drawing perpendiculars through all of those lines, connecting those lines together, and then again, the potential points from positive to negative, or in this case, from high potential down to low potential. So each one of those lines that you draw out, make sure you label that, again, this one's 5 volts, 4 volts, 3 volts, 2 volts, and 1 volt, and et cetera. So that way we know which way is the high side, which way is the low side. So you're gonna be doing 2 of these. The first one you're doing is exactly this one. So the one I was just doing over here. So that's 2 point charges, one a positive charge, one a negative charge. This is what's known as a dipole. And then the second one, you're gonna be doing 2 long strips. So basically something looks like this and this. This represents a parallel plate capacitor. So one of these is gonna be set to 0 volts. The other one's gonna be set to something like 6 volts. And again, you wanna map out the potential surfaces to then draw the electric field lines. So in my class, we just talked about this today, about the parallel plate capacitors. I'm sure you'll talk about those in Dr. or Mr. Polak's classes as well. So again, here we're looking at the relationship between these 2 quantities. So basically what this thing says is that if there's no change in potential going from one point to another point, there is no electric field. Because here, to have a change of potential, well, actually, let me go back to this one. To have an electric field, I have to have a change of potential with respect to position. So if I'm moving along a line where I have constant potential, then there's no electric field going from this point to this point. But once I move off of it, there has to be an electric field, which then brings me to that other point. So same idea as force. So if I had this piece of chalk and I move it from this location to this location, here, this has the same gravitational potential energy, so this would be the same gravitational potential if I define something similar, which means this line across here would be an equipotential surface. So here, there was no force, at least no gravitational force, which moved my particle from here to here. There was an external force which actually did that. So ultimately what this means then is potential is more fundamental than electric fields, and electric fields are actually more fundamental than forces. Because I have to have an electric field to have a force, and I have to have a change of potential to have an electric field to have a force. So all of these things are actually related to each other. So that's it. I'll see you guys in lab. Should be nice and easy.